We physicists have waited 100 years since 1916 for this photograph.
It's an area, one of the universe's most intriguing and enigmatic occurrences may well be black holes. Although they are essentially invisible to us, they are enormous creatures in terms of power. Imagine a black hole that has a mass that is between 2 and 4 million times that of the Sun. We now know progressively more about them up close and personal, having learned nothing at all about them before thanks to the study that has been done on them over the past few decades. Even if everything has only gotten stranger, Michio Kaku recently said that we have at last seen what is within a black hole. The scientific community may have overlooked some features up until now, but these new findings shed light on them. Come along as we explore black holes further and see what lies within the largest object in space. Prior to delving into the specifics of Michio Kaku's discovery, it is necessary to discuss firsts. There are still certain gaps in our understanding of black holes, despite the fact that the majority of us have a basic understanding of them. You know, black holes were predicted to exist when Albert Einstein published his general theory of relativity in 1916. Black holes were only theoretical concepts at the time. The scientific community didn't discover proof that black holes exist for another 50 years. This occurred in the 1960s when they discovered an unusually brilliant blue star that was releasing X-rays while researching the Cygnus constellation. This star was orbiting a massive dark object rather than being a stationary object. The term black hole came from the discovery that the X-rays were being drawn into the black object they were circling rather than just traveling about on their own. This finding was important because it demonstrated that black holes are real phenomena and are not the product of Albert Einstein's crazy imagination. That was all well and good, but it also meant that there was this thing out in space that we just had to learn more about. Thus, scientists from all over the world set to work. Known by the designation Cygnus X1, this black hole is situated in the constellation Cygnus, some 6,000 light-years away from Earth. It was a significant finding since it has a tremendous gravitational attraction and is around 14 times brighter than the Sun. Nothing can escape the gravitational attraction, not even light. This explains the name black hole. The idea of a black hole is equally unsettling and exciting. Nothing can escape from this area of space due to the intense gravity, not even light. Anything that approaches a black hole too closely will be drawn in and swallowed up, never to be seen again. However, the fact that they are dangerous makes learning everything there is to know about them much more important. Were we just getting started, or was this it? That turned out to be the correct response. Following the discovery of Cygnus X1, researchers began looking for more black holes. They discovered that the number of black holes in the Milky Way alone may be close to 100 million, but we still don't know for sure because they are so difficult to find. However, it appears that there are millions of black holes in our galaxy, the Milky Way, which increases the significance of studying them. So let's dissect it. Gravity will always be the primary issue with black holes. Anything that enters them will compress down astronomically until it becomes a singularity because to their strong gravitational attraction. Said another way, black holes may be thought of as cosmic vacuum cleaners that absorb everything. The idea that if a person were to fall into a black hole, their body would be stretched to the point of becoming a single line is among the most terrifying aspects of the study done on them. The patient would pass away before the final shape really took hold, and this process would be gradual. To put it simply, nobody ought to be entering one. But may we truly be in danger? They're everywhere? The nearest black hole to Earth is 1,500 light-years distant, yet that's still close enough to raise worries and questions. The first undistorted image of a black hole, the M87 black hole, was made public by scientists in 2021. The researchers took many nights' worth of pictures of this black hole, and with each one, they learned more and more about it. To construct something that filled in all the gaps, they had to stitch together the separate photographs. They were able to determine that a black hole had 3 levels in this manner. Contrary to popular belief, there is more than simply one massive void in the middle. That is not even close to how difficult things are. You have to pass through the first 2 levels of a black hole in order to even reach the empty space. The point of no return is found in the first stratum, which is referred to as the event horizon. There is no going back once you cross the event horizon, you will be drawn into the black hole. From that point on, it just gets worse. The area where light orbits the black hole is known as the photon sphere, and it makes up the second layer. The black hole's gravitational force will imprison any light that enters this area and prevent it from leaving. Ultimately, we reach the singularity, the third layer. Everything that enters the black hole is squeezed to an astronomical degree until it turns into a singularity at this point. The singularity is a moment in spacetime where the known rules of physics collapse and the future becomes unpredictable. The density is unlimited and the laws of physics as they exist today vanish at the singularity. Now, the worst part of all of this is that each black hole you investigate will be completely unique from the others. Although they often operate according to the same three-layer model, they may not work exactly the same manner. Now, if this were anything else, we could just get back on those telescopes and really examine the issue at hand. But it's not really possible to do that with black holes. Only by examining the radiation that black holes release and the gas and particles that surround them can scientists learn about them indirectly. Because everything that penetrates the event horizon is drawn towards the singularity, or it is compressed to an endlessly small point, sending a probe like the Voyager inside a black hole is not feasible. Therefore, it is not really feasible to squander billions of dollars in order to catch a glimpse every time, as the probe will just smash into oblivion as soon as it is close enough. Despite the fact that these items are actually three-dimensional phenomena, scientists are forced to investigate them in 2 dimensions due to this obvious issue. The fact that each black hole is different and that our understanding of the rules of physics is disrupted when we attempt to investigate the inside complicate matters further. This implies that the study of black holes cannot be adequately approached using the conventional scientific research methodologies. That is not to say that scientists haven't been working hard. Black holes are the subject of several ideas and explanations, and as time goes on, the complexity of the theories grows. The idea that collapsing stars constitute the source of black holes is among the most convincing explanations for how they arise. A star can no longer generate enough energy to fend against the relentless inward pull of gravity when it has used up all of its fuel. The star thus starts to collapse in on itself, getting denser and smaller as it does so. This process can go on until the star produces a singularity if it is large enough. NASA scientists focused on the center of the galaxy M87 in order to gain a deeper understanding of the nature of black holes. A violent vortex of extremely hot hydrogen gas was seen by astronomers whirling at an incredible speed of 1.2 million miles per hour. This rotating disk of gas should have violently broken apart in all directions due to its tremendous force, yet it didn't. To stop this from occurring, scientists reasoned that a massive mass centered in the galaxy's center was necessary. There was no way this enormous object, which weighed between 2 and 3 billion suns, wasn't a black hole. However, that is not the exclusive theory. Even black holes spin. In 1963, the most accurate description of a spinning black hole was given by New Zealand mathematician Roy Kerr using Einstein's equations of gravity. Kerr demonstrated that, contrary to what was previously believed, a spinning black hole will collapse into a narrow disk or ring of fire rather than a point. Because of the fast spinning, centrifugal forces would prevent the disk from collapsing. The region around the black hole is known as the ergosphere, and it is this spinning disk of matter that the laws of physics begin to break down. The fact that Kerr's solution anticipated the possibility of an Einstein-Rosen bridge, or wormhole, was its most exciting aspect, though. This is a hypothetical spacetime bridge that joins 2 distinct cosmological regions, or maybe 2 parallel worlds. According to the theory, if someone were to fall into a black hole, they would be launched out of a white hole in a parallel world and pulled down a tunnel through the ring of fire rather than being crushed to nothingness. We must examine Einstein's theory's idea of spacetime in order to comprehend how this operates. Spacetime is a 4-dimensional fabric made up of interrelated space and time, not 2 distinct things. Masses of things make this fabric to stretch, generating a gravitational field that draws other items toward them. Now picture spacetime on a piece of paper. The movement of things across spacetime can be illustrated by drawing a line connecting 2 spots on paper. However, what if you could make a shortcut between the 2 sites by folding the paper in half? This is a wormhole's fundamental concept. It's an instantaneous spacetime shortcut that links 2 far-off locations. Not only are wormholes a science fiction idea, but they are also a general relativity prediction. The reason wormholes collapse so quickly is because they are intrinsically unstable, even though no one has ever personally witnessed one. However, if an Einstein-Rosen bridge is real, then black holes might be more than simply cosmic vacuum cleaners, they might also be doors leading to different parts of spacetime. So is it possible for humans to travel through time and space using wormholes? Regretfully, the likelihood is probably not, at least not yet. It's doubtful that we could utilize a wormhole to travel faster than light, even if we could stabilize one. According to Einstein's special theory of relativity, there is an absolute maximum speed at which anything can move across spacetime, the speed of light. Perhaps still, scientists have been fascinated and intrigued by the idea that wormholes and black holes may be portals to alternate universes or perhaps to past eras for many years. The hypothesis that spacetime has shortcuts that enable travel across enormous distances or even into the past has the potential to be revolutionary. One of the most fascinating ideas in this field of research, if it could be realized, is the Kerr wormhole, so named for the mathematician Roy Kerr, who was the first to explain it using Einstein's gravity equations. This kind of wormhole is essentially a theoretical spacetime tunnel that might link two far locations, such two universes or even two distinct moments inside one world. Many people see the Kerr wormhole as a ring-shaped opening, much to the looking glass from Alice in Wonderland. Alice was sent to a realm where logic wasn't always applicable and animals talked in riddles as she passed through the looking glass. It is possible that traveling via the Kerr ring may carry a visitor to another world or era where the rules of physics are radically different from what we know. That may just be typical for the destination. As we've already touched on, wormholes as a potential route of time travel or intergalactic travel are an intriguing concept, but they're also a source of disagreement and discussion among physicists. Some have noted that because of the strong radiation and subatomic pressures at their entry, wormholes, especially Kerr wormholes, might be unstable or unfeasible to travel through. The detractors contend that the quantum forces governing radiation and subatomic particles are not affected by Einstein's equations of gravity, which are used to explain wormholes and black holes. A new theory that unites the laws of gravity with a quantum theory of radiation is required to fully comprehend the nature of these events. This is referred to as a theory of everything in the scientific community, since it is a single theory that can combine the quantum theory with Einstein's theory of gravity. Renowned theoretical physicist Michio Kaku has also spent decades developing a theory of everything. Although there are many possible interpretations of this, superstring theory is the only one that has demonstrated potential. Radiation theory and gravity are combined in superstring theory. According to the hypothesis, the cosmos is a symphony of tiny vibrating strings, which are actually subatomic particles. Various particles in nature correlate to various vibrations of a superstring, much as different musical notes correspond to different vibrations of a violin string. The idea that a string may create black holes, wormholes, and other unusual solutions to Einstein's equations by warping the space surrounding it as it moves through time is one of the most intriguing aspects of superstring theory. This indicates that superstring theory explains many of the enigmatic events we witness in the cosmos, in addition to tying Einstein's theory of gravity and the quantum theory together. But there's something about this hypothesis that, despite how straightforward it may seem at first, also makes more sense in a way. 10 dimensions of spacetime are needed for the strings to be able to vibrate according to superstring theory. Compared to the 3 dimensions of space and 1 dimension of time we encounter on a daily basis, this is completely different. Though it's hard to picture what these additional dimensions would be like, scientists have created several conceptual models that provide light on the matter. Think imagining a 2-dimensional pond full with fish that only know how big it is and how wide it is. These fish have no concept of height and have no idea what it would be like to exist in a 3-dimensional environment. The fish may perceive the impacts of the 3rd dimension even if they are unable to directly feel it, such as when rain falls on the pond and creates ripples. In a similar vein, physicists think that although we are unable to directly view the additional dimensions of spacetime, we are able to see their influence on the reality we live in. Specifically, in superstring theory, the vibrations of the strings can generate energy waves that pass through the additional dimensions of spacetime. These waves have the ability to take the form of particles with various characteristics, including mass and charge. Thus, all of the particles and forces that we can perceive in the cosmos, including gravity, may be explained by superstring theory. There's a catch, though. We are not really able to explore the additional dimensions of spacetime required by superstring theory directly because they are so tiny. The 4 dimensions of spacetime that we are familiar with, length, breadth, depth, and time, are the only ones that allow us to perform the most accurate measurements in our labs. How therefore can we even be certain that the other dimensions are real? One theory is that the extra dimensions are unseen to us because they are coiled up so tightly. Picture a tightly wrapped up piece of paper, like a cylinder. You might not even notice that the paper is curved if you were an ant moving over its surface. In the same way, the additional dimensions of spacetime and superstring theory may coil into microscopic spirals or loops that defy our perception yet influence the behavior of the vibrating strings within them. Another idea is that during the Big Bang at the beginning of the cosmos, the additional dimensions were more visible. Some interpretations of superstring theory claim that the cosmos was once a 10-dimensional spacetime with equally observable dimensions. The additional dimensions started to collapse and coil up as the cosmos cooled and expanded, leaving us with the 4 dimensions that we can see today. If this is the case, then there may be signs of the other dimensions in our environment. The superstring theory involves extremely complicated mathematics. It has made hitherto uncharted territory in mathematics completely accessible. On the other hand, the problem of a quantum black hole has proven to be difficult to solve. Despite several attempts by physicists, no one has been successful in solving this issue to far. Superstring theory has been described as 21st century physics that fell accidentally into the 20th century by Edward Witten of the Princeton Institute for Advanced Study. A major advance in physics was separately disclosed by multiple organizations last year. They discovered that the problem of a quantum black hole might be fully resolved by string theory, but only in 2 dimensions, not 10. Many physicists think that since the related equations are well defined while being challenging to solve, it's only a matter of time until someone solves this puzzle. Until then, at least when it comes to black holes, it's still too early to purchase tickets for interstellar or time-traveling excursions. One thing is evident from all of this: there are just too many questions and answers to these issues. Michio Kaku has shown how it is possible to determine the true nature of the answers to all of the wild notions. It's crucial to remember that string theory is not the only field in which the issue of endless replies arises, he added. In actuality, there are countless ways to solve a lot of brilliant hypotheses. Newton's rules, for instance, may be used to forecast the motion of a variety of items, including boulders and rocket ships, but first you must identify the object you are attempting to describe. We refer to these requirements as beginning conditions. In the same way, you have to explain to string theory what it is meant to describe. However, the Big Bang itself serves as the beginning condition for string theory, in contrast to other theories. This implies that you have to define the currently unknown conditions of the Big Bang at the moment of its creation. There are 2 methods to tackle this issue. One option is to use string theory to explain how the cosmos evolved after the Big Bang and conduct experiments to determine the original conditions at that point. Based on certain plausible estimations of its nature, string theory already has answers that explain the evolution of our universe since the Big Bang. This is a noteworthy accomplishment. Demanding that string theory choose its own beginning circumstances is an alternative and more ambitious course of action. That one is also less likely and a little more complex. Thus, we've already made a tremendous amount of progress. But Michio Kaku gives it all a different twist here. It's possible that the Big Bang wasn't as massive as first thought. He argues that contrary to popular belief, there wasn't a huge explosion. Furthermore, it didn't create the thunderous noise that one would anticipate from a bang. The Big Bang theory just asserts that there was a bang. It offers no explanation for what produced it or how it happened. In actuality, we require a hypothesis that explains the events leading up to the Big Bang. String theory enters the picture here. This idea suggests that our world may have evolved from the collision of 2 distinct universes, or that it may have originated from another universe, much like a child emerging from its mother. Wormholes are connections between worlds that resemble tubes joining 2 bubbles. There exists a possibility that we have already found proof of this umbilical cord connecting our universe to another. We could, in a sense, have been unaware that we had been living within a black hole the entire time. Consider this: it's feasible that we are truly within a black hole, and the black holes we study are wormholes to these other dimensions because we can only perceive things in 4 dimensions. Do you think there could be truth to that theory? Let us know in the comments below. If you like this video, please give it a thumbs up and we'll see you in the next one.